as Suhail mentioned, I do work at Cursor, and I don't think he knew it, but he stole my first slide. And I was on the side, so I would like to see it from up here. How many of you are Cursor users? Okay, all right, a decent number. Nathan, that's cheating. You work there. How many of you are Claude Code users? Okay, were there repeat hands? If you use both Cursor and Claude Code, can you? Okay, all right, interesting. Codex? Interesting. Other tools, primarily, as your primary driver. Oh, interesting, other tools. Okay, interesting. So if you have used Cursor, you've possibly seen this planning next moves thing. For how many of you is that familiar? It like shimmers a little bit. Okay, cool. So this isn't unique to Cursor. For the Claude Code users, I'm sure you're familiar with this view as well. So all of the coding tools have their different UI affordances for keeping you entertained, right? While they're busy preparing the response and gluing these little things together and then shepherding off all the little bytes down to the model, and the GPU is doing it. They're doing a lot of stuff. And that spinner or word iterator is doing a lot of heavy lifting. So what is planning next moves? What are all those steps with the munging of the data and the shepherding of the bytes down to the GPUs? How many of you actually would, I'm not going to ask you to do this, but how many of you would feel relatively comfortable coming up on stage and explaining what goes on behind the scenes for one of these things? Okay, all right, cool. So I can tell you a load of lies, and you will, you will walk out feeling like you understood something about how Cursor does this behind the scenes, and someone will look at you like you have 3 heads. No, I will attempt to explain it to the best of my ability in this very short period of time. And no, what's happening behind the scenes is not that your tokens are like playing chess with each other on Moltbook, although maybe, I don't know, maybe they are. What's hiding behind that is quite simply what we refer to as time to first token, or time to first visible token. And that's the delay from when an inference request is accepted until the model actually starts emitting that first output token that you see in your client. And why that matters is because time to first token is the latency that the users feel most acutely, or at least it seems that way. It's directly related to the perceived speed of the client. I think most folks in general don't really care how fast the tokens are streaming back once that response has come back. I feel like you're on the edge of your seat in that first little bit, right? You're like, oh, is it gonna work? Especially because uptime for these things in 2026 is not great. You're like, is it gonna work? Am I gonna get some tokens back? That's the edge of your seat bit. I feel like once the response actually starts coming in, you're like, okay, cool, it's doing its thing. I can like go grab coffee, I can go to the bathroom, I can come back. Obviously, fast models are fabulous. I would be remiss if I didn't say that I love Composer 2.5 Fast. I think it's a fabulous model. I think you should all use it. But it is really fast, and that part is really great too. But this piece, this planning next moves, this time to first token, is the edge of your seat bit. So why am I talking about time to first token? We're going to rewind a little bit. So I started working at Cursor in January, and about the time I started, we rather conveniently kicked off a big reliability push. And I say conveniently because I've spent most of the last decade in my career working on performance and reliability problems of various sorts. So I dug right in. And I don't know if you've noticed, but the AI coding space is a little bit competitive right now. And it's not, in my opinion, just who has the best models or the best agent harness, but it's who is the most stable and who has reliable uptime. Because it really matters when you are trying to get something done now that Claude Code is running or whatever, which, you know, it does 99.14% of the time. I don't trust these Copilot Codex numbers. That feels wrong. They feel too high. Let's not show GitHub's status page. It's okay, I used to work there. But ours, here's for transparency, our uptime from February to May 15th. I pulled this about a month ago. And I'd like to think that all of the effort that we put in to establishing SLOs in January and burning down a lot of the issues that we surfaced has led to a slightly greener pasture more recently. But, you know, uptime is great it's the bare minimum, in my opinion. It's like kind of a lower bound on user experience. And there's a bunch of ways that you can be interacting with Cursor, the client, or the CLI, or however you interact with one of these tools, and still feel like, this feels clunky, right? Like, this doesn't feel quite right. This feels really slow. I'm hitting all these errors. What's going on? So in mid-February, we, following our reliability push, a handful of folks, mostly like product engineers and some data scientists, set out to define a metric that would encompass how frequently users were running into issues using Cursor. And we called this metric degraded sessions. And this is how it works. So you split up the 24-hour day into 30-minute chunks. So you've got 48 chunks. And those start at the hour mark and the 30-minute mark. And if in a 30-minute period of time, which is kind of a long period of time that you are using the application, if you encounter an agent error at any point, then that counts as a degraded session, at any point in those 30 minutes. If your app crashes, that counts as a degraded session. If you encounter any other sort of, say, a hanging chat, whatever it is, that counts as a degraded session. If you encounter one or more of these issues during a single session, we split it up proportionately. So say you hit some agent errors 3 times and a one time, well, then it'll be 3/4 agent error plus 1/4 for a total of 1 degraded session. And what I'm talking about today is that dark blue blob, the slow TTFT overhead. But first, I want to do a little bit of an experiment. OK, so this is my experiment slide. I am not a professional videographer by any means. I'm a programmer for a living. So I'm going to start this video. It's going to pause halfway through. Do not be fooled. I want you all to raise your hand when you start wondering whether anything is actually even happening in the background. All right? All right, so I'm starting my timer and the video. OK, all right, all right. We were at about 10 seconds. That's really interesting. OK. So what did we decide that threshold should be? 40 seconds is what we decided. And here's why. There's a really good reason why, I promise, all right? 40 seconds also encompasses the actual models that are down the stack, right? Because Cursor serves a bunch of models. We don't serve only our own models. We serve Anthropic models. We serve OpenAI models. We serve Gemini models. We serve other models. You can plug in your own model, and we'll still calculate time to first token. It's just that I don't know how good your model is in the middle of that. What's its time to first token from the time our system reached out to it, and then we actually got that token back. This is measuring time to first token visible to you on the client. And so 40 seconds, yeah, it's not great. I'll give you that. But a good chunk of that is gated by the model provider. And where we started shaving off is the Cursor overhead piece. So all of the stuff that we're doing before we eventually send off the request to the model provider. And remember that a degraded session is 30 minutes, right? So you can fire off a bunch of agent requests in 30 minutes, especially like within the same conversation. And if any one of those requests is longer than 40 seconds with Cursor overhead of more than 10 seconds, then you will have experienced a degraded session. And that's more and more likely as you get to these longer, and longer conversations. And so if you're iterating with an agent for, say, like 2 hours, by the time that you're reaching that last request, the context that it's built up is huge. And so it's more likely to take longer. Yeah, big metrics are, a whole thing. There's nuance. So we built this metric mid-February. This is sort of what it looked like going into March. And even at a rather lenient 40 seconds, right, like slow TTFT was a majority factor. And so we were at, I don't know, like 5-ish% of sessions were degraded. So we set off to try to burn this down. And in March and April, we focused on this. And the goal was to get to only 1% of degraded sessions by June. So a bunch of client infra folks set off to address and app crashes. And then myself and some others went down the TTFT rabbit hole. And this is a little bit of this TTFT rabbit hole. I'm like 2 months into the job. I have some loose ideas as to what's going on behind the scenes, but like not really. So of course, being at Cursor, what do I do? Well, I ask an agent. I ask an agent, create for me a sequence diagram to walk me through the whole flow from start to finish. So I'm going to present a bit of like a slimmed down dive into how we do this. I'm going to hand wave a bunch of stuff. I'm going to completely omit entire pieces. If you would like a much deeper dive, come find me at office hours. Oh, I forgot to bring it up on stage. I am so sad. It's in my backpack. There's a piece of paper in there. It is relevant. To keep things simple, I'm going to start with new chats, clean new turns, and then we'll talk about subsequent turns later. So, at a high level, we can send a request. Tell me a punny joke about Cursor's TTFT. So there's selected context that the client builds up. This is all stuff that happens on the client before a single byte hits the wire. And we're starting to... All right. Oh, you know what? It might not even be in here. I know. I did all this planning. I brought it across the ocean, and I might have left it in my hotel room. If you find me at office hours later, I will show you this beautiful piece of paper. So it loads up all of your selected context. That's like at mentions, files that files, folders, images, terminals, everything that you're like dropping, copy, pasting into that box. It's going to build up some request context, which is like your workspace, MCP tools, Git repos, actual file contents. And then it has a model of, a sense rather, because that's a little bit of an overloaded term, a sense of a conversation state and the new action that you're taking. This is a little bit of a trimmed down version of what that request looks like. It's a gRPC request. Primarily, we use HTTP2 for streaming, and that's sent over to the agent server. Notice here that conversation state is empty, but this will come into play a little bit later. So this is how the agent gets its request. And then immediately on the agent, it returns a heartbeat so that the client knows, OK, it has received the request. I don't need to retry getting a new connection to the agent, and it just sits there and waits. At this point, the agent does a bunch of stuff. So it will validate that you are who you are, and you have access to Cursor, and you have access to this model, and you can do the stuff that you were saying you were doing, and you have enough money in your account to pay for the tokens that you're asking to use. And then it'll do this thing where it'll split the stream. So HTTP2, you can split the stream and send specific bits of information over that multiplexed stream. The two important ones, there's a bunch. The two important ones here are remote execution. So if the agent needs to do some kind of tool call back on your machine, it will use that stream. Or remote KV. So we do a bunch of blob shuttling back and forth of context, file data, all of this stuff. That goes over that stream specifically. Again, hold on to that, but I will bring it back into play later. All right, and then the agent builds up the model in the prompt engine, so that's telemetry, prompt logging, that sort of thing, builds the actual prompt, so what you associate with agent harness, and then it sends it to our inference proxy. And that's a little bit of what that request sort of looks like. So there's a whole content blob for all the system prompt, blah, 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 and then the actual text that the user typed in. And then our inference proxy is what ultimately decides where to route the request based on the model, capacity available. I can talk to you for a very long time about model routing. I'm currently helping that team out. And this is a little bit of what it ends up looking like. So we have our first-party model composer as a model option, and then we send requests also to the other models. OK, and then back, once we actually get a first response from the model providers, if we get a response, because also their uptime is like, And finally, we stream everything back. I know, it's taken a long time to get here. So we're streaming everything back, and that Y is the first token. That's what we are going to register on the client as the first token. We have done it. We have acquired a token. Very simple, not complicated at all. Here's a quick overview. And now that we've set the stage, let's talk a little bit about some of the wrinkles we ran into. We had missing telemetry. Who's run into this problem where they're like, oh, let me optimize this thing, and like you have no idea what's even going, that's good. There was not a lot of telemetry. So where we were measuring time to first token was from the client. So when you kick off a turn, we start a timer. And it does all the client building of the context, sends it off, shepherds it off, and then only once the token is successfully received on the client, we stop the timer. But we don't send the event yet. We only send the agent turn outcome once the turn has ended in some way, whether it's been unsuccessful or it has been successful. It's only at that point in time. So it's a little bit delayed, the data on TTFT at this point, but it's also just like merged into a smattering of other event-type information that we send to our analytics system as a result of that message. And we also had telemetry around actual model TTFT. So from the moment the request is sent from our inference proxy to the providers, we keep pretty good tabs on what's happening there. Mostly because unless it's our own model, it's a little bit of a black box for us. But that was it. This big blob, who knows? Stuff is happening in there? I don't know. We could see the 40 seconds. We could see the model slice of it, but we couldn't see it. So what did I do? Well, I work at Cursor, right? So this is where, again, I pulled out my little agent, which felt a little meta. It's like, tell me about how you are you. But I had it walk the flow with me, and this is where the piece of paper would have come in, because I'm still kind of an analog person, so I had it generate for me an entire sequence diagram of the entire flow, and it's very vertical. It's like half my height, because I went to Staples and I had them print it for me. Yes, it is a personal failing. And from that, I told it, here, tell me all the places where we have the instrumentation and where we do not. And then I told it, well, where should we have instrumentation? You're probably smart enough, you should figure that out. So I went out and figured that out. And then finally, we had all of these chunkier, important pieces in Datadog. We had all the custom metrics, and we could see the data, and we could look at the percentiles, and it was nice. But then the other thing that was really interesting about this problem, and again, this goes back to whole, like, it's 30 minutes. Anything can go wrong in 30 minutes. That's like a really long period of time. We needed to really be thinking about the tail and bringing the tail back in and reducing the variance. And that would probably stand to improve degraded sessions the most. Because actually, if you looked at the P50, it wasn't so bad. Like, the median was like actually pretty good. But again, remember, like, longer and longer conversations tend to get longer and longer model TTFT, or TTFT in general. But any outlier edge case, say at some point, Anthropic goes down partway through your half-hour session, but only for a blip, so we retried, so you eventually got your response. Well, now you have a degraded session. So we were trying to think of what is happening at the edge, how do we bring that in? And of course, okay, what's bad that happens at the edge? I sent an agent off, and I sent the agent off, and it went spelunking, and it came back with a very, 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 very long list of mostly completely implausible things to do. Turns out when you set an agent loose on solve this performance problem, it's not very, you have to coax it a little bit still. This is only like half of my agent chats that have TTFT in the name over the last like several months. And what it came back with was that returning users over HTTP1 with blobs out of cache was the worst case. What the heck does that mean? Mode, you have said none of those words to date. Thank you for noticing. So the cohort, in general, in this case, their experience at the P99 was a 57-second TTFT. Quite terrible. And over HTTP2, interestingly, it was only about 9 seconds, and only 1 second when the blob was in cache. So this felt like something that we needed to fix. And the reason that, the HTTP1 thing, we really got to do something about that. So there's people out there who don't have nice things, and they use VPNs like Zscaler. And it doesn't support HTTP2. And I feel sorry for those people, because we have to do things like write our own HTTP1 sort of BiDi approximation protocol so that we can serve these people. But really, Zscaler should just support HTTP2. So HTTP1 is net worse because it does this like weird polling thing. But also, here's the bit about the blobs. So once the agent is done with a particular bit of processing, it sends back a checkpoint. And in the checkpoint are blob IDs. And it says, I have cached this blob of data over here on myself locally and in Redis, and this is the blob ID associated with this blob. So it tells the client, this is what I know about, so that the client can be a little bit quicker with telling the agent, hey, like, refer to this blob ID. And it's like, oh yeah, I know that blob ID, I've seen it before. Great. And as of today, there's no affinity between clients and agent servers. So between turns, even if it's the same chat, you could be connecting to a completely different agent server. So that's why we have Redis, because then when the request goes from the client to the agent doesn't have any sense of what the heck these blob IDs are that you're talking about. I don't have those, I've never seen those. What are you talking about? Well, it can go to Redis and go and get the blobs. And then it's like, okay, cool, all right, I'm in a much better spot, I know about this. But if you come back, the TTL on the Redis is only 30 minutes. So if you come back 30 minutes and 0.1 seconds later, well, you are out of luck. The blobs have fallen out of cache. And then we do this really terrible thing where the agent server has to be like, but I don't know about this blob anymore, help. And we do this sending back and forth of all the blobs. And that is how we land at a 1-minute TTFT for the poor people on HTTP1. Okay, some of the optimizations that we did. The first thing was we just increased the Redis TTL. I see someone cheering. Yeah, we just increased it. We took it from half an hour to 2 hours, did some math. You can see here that after 30 minutes, P99 TTFT falls completely off a cliff and goes to 37 seconds. That's quite terrible. So we moved it up to 2 hours. We figured we'd gather about like 10 million additional turns that wouldn't fall off that cliff. That was great. And then we just had to figure out, okay, how much extra Redis space do we need? What's reasonable? Blah, blah, blah. And then we did this thing where we decided to prefetch blobs and shepherd those over. So after the 2-hour mark, if we think you're going to resume a turn, we preemptively send you all the blobs. So we just cut all of the blob shepherding back and forth out. And that's a little bit of what it looks like. And then we did this very simple thing that is so deeply human, where we just eliminated duplicate work. So how many of you have just found the same thing happening twice, being calculated twice in your code base before? Yeah, it's so satisfying to delete. How many times was that written by a human? It's not just the robots. So we shaved off a good 10 seconds by just eliminating duplicate work on the client. That was just there. But also, like, that just happens organically with time. It's a little bit inevitable with growth, especially like hypergrowth that we're experiencing. A little bit of the results. So you might be thinking, Mode, we're in June. Did you do it? Did you get to 1%? Sort of. We cut it down by a significant margin. But what the most annoying part of this whole thing was that none of the improvements showed up in the metric in a really obvious way. You'd think we fixed all these terrible P99 edge cases. Like, it should have just fallen off a cliff. It did not. It did not. And there are sort of 2 reasons why. So the first was that 2 of our 3 fixes shipped on the client release train, which, please, if you are using an older version of Cursor, update. Dear God, please just update your version of Cursor. Okay? We fix stuff all the time. It gets so much better. Please just fix it so that we can get statistical significance on the experiments we're rolling out. Okay? I need that. Please. My goals are tied to this metric. But that was part of the problem, is we shipped all of these things, and it took like 2-ish weeks before it got into the hands of people. And what we didn't do is we thought this would be such a steep fall off a cliff that we didn't need to A/B test them. And we were a little too optimistic, and turns out there's a bunch of other stuff also going into client releases at the same time. So it didn't show up as clearly as we would have liked. But then the other wrinkle, which had me thinking about all of this stuff, and sort of what the point I want to land today is, that degraded sessions, is a really big, opaque composite metric. And it's great as a top-line sort of health report that you can talk to product people about, that you can talk to leadership about, but it's really terrible at steering an actual investigation. And we would quickly realize that in order to be able to dig in and see, like, why is TTFT slow, we needed to be able to easily and reliably tie those two pieces together. And because they weren't from the same set of data points, it wasn't just like Datadog metrics feeding into this metric, making it all, these were disparate sources. We were struggling to align the two. It just wasn't what we expected. And the more we dug into the metric, like, what is counting in degraded sessions, the more we found stuff and nuances that, like, were not actually captured in there. So retries all counted in degraded sessions. If we retry 3 times, because I'll pick on someone other than Anthropic, OpenAI is down, then ultimately your request was longer, right? But you probably got a better experience because the request eventually came through and we started streaming tokens back to you. That was probably better than us just erroring out at first. Same with throttling, right? We, depending on load, if we are in a very, very high load moment, we will throttle connections just to gradually slow them down enough that we can process more so that everyone as a whole can have a better experience. That's ultimately a better experience than just saying, 429, better luck next time. And none of that nuance was captured in degraded metrics, in degraded sessions. So the core concept I want to leave you with is Goodhart's law. So when a measure becomes a target, it stops being a good measure altogether. And I think this is particularly important in an agent-driven development context, because there's a dozen or more changes that the agent could have made to speed up time to first token that wouldn't have actually materially improved the experience of our users. And in the end, what actually really mattered was us staying true to what we thought made sense from a product perspective about improving what felt like a degraded session, and we didn't stay married to the metric. We still kept a good arm's length. Yes, this is a goal. It's helping us figure out what we should be working on, how folks are generally feeling, but we still kept an arm's length. We were still able to say, like, yes, we shipped very important improvements. So, to do a little bit of a full circle, I think one of the most powerful levers in this environment right now, where we are all building AI interfaces, is a simple UI affordance. So to bring a little bit full circle, I present to you what we see internally at Cursor when we issue an agent request. So you can actually see all of the things that, okay, it's a demo mode. The timing is not correct, obviously, because I had to make it do the thing. But that's what we see internally. And in my opinion, I think we should be making something like this a lot more visible to folks and show that all of the work behind the scenes that's actually happening there. So we are always planning next moves, and if you are planning your next move, see what I did there? We're hiring. Find me at office hours. I'm sorry I went over time. Thank you, everyone.